So welcome again. You're all joining us in Linear Algebra 2, Lecture 3. Huh? Idia corrupted because I forgot it. Yes. Yeah, but you're all here, so it's not extremely important, and we have our uh, nice notes we're writing right now. We mentioned the formula of the terminal we saw last lecture, and the notion of an eigenvalue. We had another example, very ugly one, just ugly one. We managed to go through it, and then a couple some notes. First of all, this determinant is called the characteristic polynomial. The roots of the characteristic polynomial are actually the eigenvalues. One can see that on one hand, one eigenvalue can appear more than one time in a polynomial as order greater than one. On the other hand, there are matrices at least above R, without eigenvalues at all because the polynomial does not have any roots. And thirdly, when it comes to a triangular matrix, the determinant is the multiplication of the elements of the diagonal, meaning that the eigenvalues are the elements of diagonal as well, because they solve PA is 0. So that was no, half an hour in half a minute for the recording. Let's make it a habit. When we start the lecture, you always ask, did you start the recording? No, I started, or I started, but we will not miss it again. When you start the lesson, and we're coming in from the break, so stop it as well. Okay, that was the third thing I wanted to write down explicitly. And what else did I wanted to say before we move on? No, I think it's good. I want to explain and maybe do a little example about the eigenvectors. How do we find the V from the AV's lambda V equation? Before we go there, any other questions about what we've already written down? Okay, so finding the eigenvectors. So after when we have the eigenvalues, and we can find the eigenvectors of every eigenvalue. By solving the definition, the equation in the definition itself, by solving AV is lambda V. For example, for instance, we saw that lambda 0 is an eigenvalue of A 1 to 9. Let's control C and then control V. Huh? Ever, yes. I mean, in the WWF, WWE should be a guy that's its power move. Control C and Control V. You have Rey Mysterio, 619. Don't actually remember it. The Rock. Ching ching bing bong. You have Control C, Control V guy. Big Show. There was one moment when they said, you know what, it's all fake. I don't know how old are you, but when I was young, the WWF was not considered, but they showed it as something real, like real wrestling. I mean, all the soap opera the in the background is something else, but the wrestling itself was true. And it was like a big announcement, it's actually fake. And everyone didn't care. Just moved on, continuing buying tickets and cheering up the dude with the chair. It's fake, so what? It's still fun to watch. Okay, we saw that 0 is an eigenvalue of this matrix. So we actually solve AV is lambda V. V is vector with 3 elements. The multiplication will be defined. So we can write ABC or XYZ or whatever you like. There are different methods to find the eigenvectors, but they're all actually the same. This is the equation everything is based on. Fs multiplied by XYZ. We know how to multiply matrices into vectors. So we get actually, let's start it in 2 steps. First of all, we get x plus 2y plus 3z, 4x plus 5y plus 6z, and 7x plus 8y plus 9z. And on the other hand, just zeros. So a system of 3 equations, 3 variables. It's a linear one, of course. We know how to solve it down. So let's say from the first equation, we have x as minus 2y minus 3z. And we get following equations. To plug it in. And the others have 4 minus 2y minus 3z plus 5y plus 6z. If you want to write down a matrix and eliminate some of the elements, it's totally fine. Solving a system of equations is something that I know that you know, so it's not that important how you do it. If we arrange it a bit differently, we get minus 3y minus 6z. And here we have minus 6y minus 12z. So we have y is minus 2z. And then x is minus 2y minus 3z, which is actually minus 2z minus 3z, which is z. So the solution or the eigenvalue vectors are z minus 2z. Z, for example, oh, 1 minus 2, 1. If you multiply this vector by the matrix A, you get 0. Seems true. Yes, it's an important thing to say. I want to say it in my own words. Intuitively, for every eigenvalue, there are infinite infinite number of there's infinite number of eigenvectors. Solving the equation AV is lambda V, we know that such V exists. And when a system of equations, a homogenic one, homogeneous seems the G or G, homogenic one, because it's only zero. It's always zero because you can put the lambda x, lambda y, lambda z on the other side of the equation. If an homogenic system of equations, linear equation of course, has one non-zero solution, it has many, because the solutions for homogenic system of equations are vector space, linear space. I don't know exactly how to say it. You multiply it by some scalar, you summing vectors like that, you get the same. Multiply by a, it is zero. Multiply, if, more precisely, multiply by a minus lambda I is zero. Yes, because a v lambda v is actually, let's say, note. You want to save it? No, but let's save our. Yeah. Oh, I'm gonna save it. For the record, didn't save it. Everything is bad. Um, linear 2, Mandamach, Tashapu. Okay, that's the. Why do I have two different files here? Whatever. Linear algebra 2, lecture 3. A lot. Okay. Note that the eigenvectors are the solutions of the homogenic system of linear equations skew a minus lambda I or lambda I minus a, v is zero. We know the set of solutions of homogenic system of linear equations is a vector space. The vector space of all eigenvectors of eigenvalue lambda is called the eigenspace, מרחב עצמי in Hebrew, and is denoted with E lambda because eigen, or V lambda because vector, whatever floats your boat. Let's be a bit more precise. Zero, on one hand, is not an eigenvector. By definition, AV is lambda V when V is non-zero vector. Zero cannot be an eigenvector by definition. On the other hand, every vector space contains zero. Without zero, it's not a vector space. So, this sentence is a little, don't say exactly, a little mistake now. But if we look at the set of eigenvectors and that's it, we get almost vector space. We are missing zero. So speaking correctly, precisely, one can say that the eigenspace of lambda is the set of all eigenvectors of lambda and zero. You add zero to the set and you get a vector space. Yeah, so so if u and v are eigenvectors of the same lambda, and let's say alpha is a scalar, then alpha v, alpha u, alpha u plus v is also an eigenvector, pardon, of the same lambda. So as I said before, intuitively, a vector space contains an infinite number of vectors. Talking real or complex, it is correct. But generally speaking, we know from our previous course that one can talk about if the field above it, everything is going on. One can talk about Z3 or Z5, some finite field, and there, let's say that we have a finite number. But it's basically, and when it comes to the examples we give here and here in the practices and the homework, most of the time it's R or C, and there it is actually there are a few number of eigenvectors. Because, as I mentioned, when we solve an homogenic system of linear equations and we have a non-zero solution, we're going to multiply it by some alpha and we get another solution for every alpha you want. So speaking of the system of equation itself, it means that you will always have at least one free variable. Here it is z. We can write x and y as an expressions of z, and z is the free variable. You can plug in whatever I want. The system will work. Later we'll discuss this number of free variables in the systems of AV of lambda v, corresponding to lambda, and on the other hand, the power of lambda in the characteristic polynomial. These two numbers, the power of the characteristic polynomial and the number of free variables in the system of equations, are both very important numbers. I have a lot of things to say about them. But for now, we have other things to do. So, any questions about what we said here? Okay. So I want to say another thing. I don't remember we said it in the end of our last lecture. I don't think so, but write it down and you tell me. Let's have a proposition. Um, let A be a matrix of order n on n. What do I want to say here? And let some lambda. No, that's not what I was. That's way. Um, 0 is an eigenvalue of A if and only if A is not invertible. Or A is invertible if and only if 0 is not an eigenvalue of A. Let's explain it, let's prove it. We know that 0 by definition, yeah? 0 is eigenvalue of A if and only if there, I mean, you can write it down with the eigenvectors or with the determinant, meaning the characteristic polynomial, it will be the same. So let's write down like that. If and only if 0 is a root of the characteristic polynomial. When we plug in 0 in the characteristic polynomial, we get 0. The characteristic polynomial is 0 by the definition of the characteristic polynomial if and only if the determinant fs or a minus fsi is 0. And that's right if the determinant of a itself is 0. Then we've already seen before, determinant of a is 0 if and only if the matrix is not invertible. Write it down. And we know that the determinant is 0 if only if a is not invertible. I want to add something from the future, the near future of the course, but let's write it down here. Note, generally, the determinant of A is the multiplication of the eigenvalues. When A is triangular, determinant is the multiplication of the elements of the diagonal, and they are the eigenvalues, as we mentioned before. But generally speaking, the term, missing the R here, is true. The second, determinant is the multiplications of the eigenvalues. It's not an immediate statement. We can prove it using some of the further subjects we'll go through. But right now, from a different angle, explains our last proposition. I mean, if one of the eigenvalues is 0, and you multiply all the eigenvalues, multiplying 0 with something is 0. So we get a determinant is 0, and the matrix is not invertible, but if A is invertible, it works as well. The determinant is the multiplication of the eigenvalues, and as I mentioned, when we get to the exact subjects that talks about it, we'll mention it again. Yeah, question, first of all. Um, the aside, the like the form of getting what you can. Um, uh, non-verbal? Yeah, I'm trying to. We're thinking together right now. Um, First of all, about the phrasing, one can say non-invertible or something like that. Yes, you can. First of all, for the phrasing, you can say singular. Singular means non-invertible. And for notation, I don't think. Do we have a notation for invertible matrix? We don't. For invertible matrix, we don't have.
I mean,
It's the same.
I think you can describe it as like there's a symbol for Gaussian elimination, right? So
I don't think I know such one. There is a notation one can denote the set of all invertible matrix. It's called a GLN. So instead of invertible, one can say A is in GLN. It's
um, okay.
not so good.
For another question, I'm a bit lost. So we said that eigenvalues are what we multiply eigenvectors with, like a vector A multiplied by an eigenvector minus the eigenvalue multiplied by the eigenvector
Is zero.
is zero.
Mhm.
And then we took out the vector, so it's A minus
Lambda I.
lambda I. And then we said that it's the same as saying that the determinant of A minus lambda I equals zero.
Yes.
Okay, and now
And we already said it in the previous week. Because when you, as you said, move it to the left side and we plug out the V, saying that a matrix multiplied by vector is zero when the vector is not zero, meaning that the matrix is singular, is not invertible. And the non-invertible singular matrix has determinant of zero. So in order to find the eigenvalues, we solve the determinant of lambda I minus A is zero. Any more questions? Yeah. If. First of all, I'm right. Not just by being the lecturer, but because that's how you pronounce it. And secondly, why do you ask? Because they're homogenic? Yes. How do you actually say it? Who says chief?
the creator.
The creator? Well, okay. Let's move on. We don't have much time to our break, but let's start the next subject force. It's still connected to the subject of eigenvalues, etc., etc. We call it similar matrices. So let A and B in F and on M be two matrices. A and B, now definition is a bit weird, but as we walk through the subjects and walk through the material, we'll see why. A and B are called similar, whatever. And we can denote something like A B if there is an invertible matrix. What? It's a definition. So yes. Similar if there is an invertible matrix P such that A is P, B, P minus 1. When you write it down, P from here, P minus 1 from there, you get A. So this is a bit not connected to whatever you already said, but as I said, when you go through the um, when you go through the material, the break, and then move on, we'll see why this definition is important. First of all, I want to write down some of the properties of similar matrices, and we'll see how many time we do have such time to prove some of the properties.
Um,
Yeah.
During our first semester, we didn't learn a new decomposition element for that.
No.
No, we did learn a new decomposition.
A lot of things, but among them, the helium decomposition. No, it's not important for me here, at least. Probably for your life, I don't know. I don't know going to work. Yes, the compositioning matrices. Properties. Okay, let A and B be similar matrices. Oh, let A, B be similar matrices. First of all, similar matrices have the same determinant. Secondly, they have the same trace. Trace is the sum of the elements of the diagonal. Why don't you write me trace? Trace A is trace B. Third, they have the same characteristic polynomial, so they have the same eigenvalues. No, it's X, or something like that.
Um,
Yeah,
this uh, this property is symmetric.
it's more than that. It's an equivalence relation. Yes, I write it down.
Yeah, no,
Sure.
it has the same matrix, or it doesn't have the same matrix.
No, it doesn't have the same P. I mean, it will be P minus one. Yeah. Trace is the sum of the elements of the diagonal. What else can I write here? They have the same rank. Trace. Trace is the sum of the elements of the diagonal. Is A11 plus A22, and so on. Four, they have the same rank. Rank is the number of non-zero rows after you eliminate the matrix. What else can I write here? Okay, it's clear from three. So write down there. So they A and B have the same eigenvalues. I'm not saying anything about the eigenvectors, which are defined by the equation A v lambda v and B v lambda v. A and B are different, they're similar, not equal. Can be different eigenvectors, but eigenvalues are the same. And moreover, furthermore, whatever, matrices similarity. That's how you write it, or you add an I, similarity, whatever. Mesh similarity is an equivalence relation. Meaning that every matrix is similar to itself. If A is similar to B, it actually goes to the opposite direction. B is similar to A, and if A is similar to B and B is similar to C, then A is similar to C. Any questions? Okay, we'll try, and I can try to answer. Um, let's prove one. Let's prove one of the, I don't know, seven things we wrote it down. So any preparation? What do you want us to prove? 1, 2, 3, 4, A, B, C. Let's start with A. Okay. Prove when it comes to A, we need to find an invertible matrix P such that A is P minus 1. It's the same A here. We're going to try to prove our little A. So, who's going to be? Which P is it? That satisfies A is P minus 1. Yeah, of course. Indeed, P equals I. And do the job. I said hero. Is satisfies. Satisfies. Let's write down. Satisfies A is P minus 1 and is in rollable close. So that's A. Probably the easiest one. Yeah. It's A, but all 1, 2, 3, 4 are the same. I want to prove one. לבריאות לחיים טובים. One of let's go with one. To prove that we prove one, and then we'll have our 15 minutes break. We want to prove that a determinant of B is the determinant of A. And we know that A is P, B, P minus 1. So the determinant of A is actually the determinant of P, B, P minus 1. Now, the determinant of multiplication is the multiplication of the determinants. And yet again, different property of determinant. We stated before that the determinant of P minus 1 is 1 above the determinant of P. And how convenient. The determinant of P is cancelled, and we stay with the determinant of B as we wanted. Any questions? Okay, so let's have our 15 minutes break. When we come back from there, first of all, you have to mention me too. So, okay, it's 5:04, it's 6:04. Actually, the water fountain in the square downstairs is actually working. You can, you know. The bathroom. Ah, the bathroom. Well, You go for it. So all this matrices similarity leads us to the following subject. It will be confusing in the first 2 minutes, but then everything will get a nice shape. It's called write it down with you, diagonalization. Diagonalization. Yeah, it's a nice word. And I already started the recording. Yeah. Ah, very nice. Very frightening, I have to say. Some horror film. The tablet is creeping me. Diagonalization. Okay. Mhm. Diagonalization. Missing an A here. Okay. Let A be some matrix of order n. A is called diagonalizable. You can make it diagonal, right? Diagonalizable if it is similar to a diagonal matrix. Different words. Different words. A is diagonalizable if there are matrices P invertible and D diagonal such that A is PD P minus 1. The diagonalization is the process of explicitly finding such P and D. Now, why is it important? Why is it useful? Two L's or just one L? One L, right? Useful. And important. Um, there was one time, and don't can recall it very well, someone explained me how you organize the adjectives in English, color before number or vice versa, whatever. So I don't know if useful is more important or it was useful. Let's have a simple example. A simple motivation. It's not the whole picture, but we can start from here. A simple motivation. Let's say we want to calculate a to the power of large number, 1,000. Okay. For example, we have a video game, and when a character changes its placing, we actually multiply the current vector of, I don't know, the north for south, east for west, up for down, etc., with some matrix. And when the character takes 1,000 steps, we actually multiply its current position with 1,000 the matrices. So we want to calculate a to the power of 10,000. First of all, it's important to say we don't actually have to multiply the matrices 1,000 times, because when you first multiply a with a, you get a squared. And then you can take a squared and multiply it by itself, getting a to the power of 4. And then a to the power of 8 and 16. So when it comes to talking about O of what? How many operations of matrix multiplication do I have to do here? So it's basically log on basis 2 of the power. Not exactly for 10,000, we get 512 with 9 multiplications, and then you add 256, and then 128 is probably 11 or 12 matrices multiplication, and you get the a to the power of 1,000, but it's a large number when the power is a large number itself. Every multiplication of matrices is a complicated thing because every row and column we multiply and then we sum. It's basically O of n to the power of 3 because every matrix is n on n and it has n squared elements, and every element needs the multiplication and the summation. It's a bit smaller than that, but it's not our subject. Now, if we have A is P D P minus 1, we get that A to the power of 1,000 is P D P minus 1 to the power of 1,000, which is P D P minus 1, P D P minus 1, and so on for 1,000 times. And now every P and P minus 1, when they meet each other, they cancel each other, and it becomes the identity matrix. And we don't have to write down the identity matrix when it comes to multiplication. So we actually have P D to the power of 10,000 and P minus 1. P minus 1. Why is it? Oh, it's the WhatsApp, whatever. Where is it? Where are you? So what's so funny? Ah, yes. You stay away from the board, so we won't diddle you. If you look closely, the board is somewhat oily. Yeah. So, why is it better? Calculating the power of a diagonal matrix is very easy. We just calculate the powers of every element in the diagonal. So, something like this. Did you buy flowers?
What are
Do you eat it? Do you smell it? Do you what?
This is basil.
Yes.
Yeah, that's oregano.
Oh, it's for the great for pizza.
This is a little, I don't know what it is. This.
My wife has a lot of them. We cook them all the time. It's convenient.
They're all my favorites.
In winter, they actually survive. When summer comes, we all dry out and die. Okay, so as I started to say, because D is diagonal, calculating D to the power of 1,000 is very easy. So instead of calculating the a to the power of 1,000 or million or trillion, one can go through this diagonalization process. We'll shortly explain how to do it. And then multiply P with D to the power of 1,000, million, trillion, and multiply P minus 1. Instead of a lot of multiplications of matrices, we are going through the diagonalization process and another 2 multiplications with P and P minus 1, which when the matrix and the power are both very big, should be quicker and easier. So now the question is, how do we actually do this diagonalization process? And we have to answer two questions, actually. The second one is, how do we diagonalize a matrix? But the first question, or basic one, is how do we know what conditions the matrix should suffice that it should be diagonalizable from the beginning? Right? Not every matrix is diagonalizable. How do we check if a given matrix is diagonalizable before we start the diagonalization process? So these are the our two questions. How do we answer those questions? I want to answer them, and then we'll have an example. It's a theorem. Don't think we're going to prove it, but we're going to write it down. Theorem, let A. What? Yes. If you're not the diagonal, you get 0. A. Yes, triangular both ways, upper and lower. Let A be a matrix of order n. A is diagonalizable if and only if there is a basis. There is a basis of Fn containing. That's alright. Containing, yeah. Only eigenvectors of A. In this case, that's for the second question. The matrix D, we want to find the D and P. Matrix D is the diagonal matrix with the eigenvalues of A in the diagonal. And P is matrix with columns, and the matrix P and the eigen is, I want to write it down differently. Semicolon. P is a matrix containing, having, whatever, the eigenvectors of A in its columns, respectively. Let's write it down. I don't think so. Without the L, respectively. No, it's with the E. Respectively to D. What I mean with respectively to D, we'll surely have an example and we'll understand. So I'm not proving the theorem. Why diagonalizable is if and only if there is a basis of eigenvectors of the vector space. But we'll have two examples. First of all, let's have an example where there is a basis, and secondly, we'll have an example where you don't have one. And then we can continue the first example with finding D and P. Okay? examples. Let's start with A is the numbers you love. 21 and 6 and 7. Yes. No, it's enough. I'm writing down the one. Let's just be one. All right. So this is A. What are the eigenvalues of A? First of all, we find the eigenvalues. So the polynomial characteristic polynomial of A is 0, and this is the determinant of lambda I minus A or A minus lambda I, whatever. This is the determinant of lambda minus 1, minus 6, 0, and lambda minus 7. And we have here lambda minus 1 and lambda minus 7. One can say, as we mentioned before the break, A is triangular, so the elements of the diagonal are the eigenvalues. First of all, the eigenvalues. Secondly, we find the eigenvectors. So our main equation is AV equals lambda V. It doesn't matter because it is 0. So minus here, minus there, it's the same. Huh? Yeah. AV is lambda V, which is 1607 multiplied by some vector V. General one can write down X and Y, A and B, alpha and beta, whatever. Lambda XY. And we know how to multiply matrices with vectors. It's X plus 6Y, and this is just 7Y. This one here is lambda X, lambda Y. One can write down explicitly as a system of equations. Must. So two equations, 1x plus 6y is lambda x, and 7y is lambda y. Internet connection is unstable. That's what the Zoom just told me. First of all, it's not my internet connection, it's the university's one. It's not my fault. And secondly, as long as the recording is working, we are all here. It's not very important. It's all good. So what do we get for lambda is 1? Of course, it is a Hebrew. Lambda is 1. Get x and y. So y must be 0. 7y cannot be y. My default is f is r, field of real numbers. I mean, one could say, hey, in Z7, it is not right now. Long arrow not. מה זה אומר? Long right arrow. Y is 0. So the eigenvectors are x, whatever you like, a free variable, 0 instead of y, for example, 1 and 0. What do we have for lambda is 7? I control C, control V, and change what we need to change. For lambda is 7, we have 7y is 7y, and x is plus 6y is 7x, meaning that y is x. So the eigenvectors are xx, for example, 1, 1. Now, we do have a basis of F2 or R2, whatever, containing only eigenvectors. So you can have R if you want. It's simpler. So, by our theorem, it means that A is diagonalizable. Yeah. I mean, F is the field that we are working above. Default can be R. It's all good by me. But we will talk about the complex number from time to time. And a basis of R to the power of 2, two vectors which are linearly independent. It's enough for a basis. In R3, you need 3. In R6, you need 6. And so on. Yes. We write down linear combination equals to 0, and we show that every coefficient is 0, must be 0. When it comes, yes. One can, first of all, you can write it down as matrix rows, performing elimination, and then if you get row zeros, they are dependent. If not, they're independent. You can do it also using the columns, looking for a free variable. And when it comes to two vectors, it's much simpler. If they are not multiplication of each other by some scalar, they are linearly independent. In R2, they are bases. So we do have bases. So by our theorem, the matrix A is diagonalizable. Now we can move forth to the diagonalization process itself. How do we find P? And now do we find D? So as we mentioned, in this case, the matrix V contains this diagonal one, contains the elements, its elements of the diagonal are the eigenvalues of A. And we have a bit of freedom here. I mean, one can say, okay, D is 1, 0, 0, 7. And one can say, you know what? It's 7, 0, 0, 1. And both are fine. Both are good. But now, when you write down the matrix P, and as we said, its columns are the eigenvectors, it should be written down respectively to D. Meaning that if we have 1 as the eigenvalue that we put in the first column of D, so the eigenvector of 1 should be in the first column of P. It was 1, 0. And if we put 7 in the second column of D, then the eigenvector of 7 should be in the second column of P, which is 1, 1. because we put 1 in the first column of D, so we have to put its eigenvector in the first column of P. That's what I meant by respectively. And yet again, first of all, D can be written in this specific way case in 2 ways, 1, 7 or 7, 1. In the general case, you have n eigenvalues, and you can order them whatever you like, however you like, in the diagonal. So it's n factorial options for D. In many cases, there are eigenvalues that appear more than one time, as we mentioned before the break. So it's a nice, not very hard, combinatorial question. How many different Ds we have? When it comes to P, we intuitively have infinite number of good matrices. I mean, the 1, 0 as an eigenvector of the eigenvalue 1 here is just an example. Every vector looking like X and 0 is a good one. You can choose, I don't know, whatever number you like at 0, and it will be fine. The same for the second vector. So we do have more than one D, and we have intuitively infinite number of P's, but D is, say it again, D diagonal matrix. In the diagonal, we have the eigenvalues of A. P is an invertible matrix. In its columns, we have the eigenvectors, respectively to how we put the eigenvectors, the eigenvalues in the matrix D. Because we have bases of eigenvectors, we know that a matrix with columns that are bases of the space, then P is invertible. So now we can, for example, let's write it down in a different color. Let's say purple. A to the power of 1,000 is D to the power of 1,000, P minus 1. And it is 1, 0, 0, 1, 1, 0, 1. D to the power of 1,000 is just, because it's diagonal, the elements of the diagonal to the power of 1,000 and P minus 1. Now we can see that when using diagonalization to calculate really large, really big, really high powers of matrix, one, first of all, need to go through the diagonalization process, meaning finding the eigenvalues and eigenvectors and writing down P and D, and then calculate P minus 1, and then multiply P minus 1 with the D, and whatever you get with P. So I'm not going to finish the calculation here, but as we mentioned, A is very big and the power is very big, it's probably easier to do so. Yet again, see an example shortly. Not every matrix has such D and P. Not every matrix has a basis of the space containing only eigenvectors. But for the when it does work, the process looks like this. Of course, when it's 2 on 2, a matrix of order 2, it's much shorter than matrix of order 5. But yet again, matrix of order 3 are the best examples. Not too short, not too long, just like call it autumn. or spring. I mean, it's nice outside, not too cold, not too hot. I don't know if you are following the forecast, but they promised some big rain. Okay, in the weekend. Our our favorite seasonal flooding when it comes to old neighborhoods in Rishon LeZion, etc. Um, 2 years ago, 2 years ago, I was praying shacharit, and I went out from synagogue, and my car was in the other side of the road, and the sidewalk itself, the pavement was okay-ish, and having blunt stones, you have an additional like 2 or 3 centimeters, but the the road itself was actually a little river. So I went to the car, and I have to go in to teach. But then I checked my shoes. They were not. I was swimming inside them, so I went quickly to my home and replaced it. Synagogue afterwards was flooded. All the chairs and the books. It was a bit of a mess. Yeah, it's probably happened as well. If the forecast is true, if there's going to be a big amount of rain, promised even 200 millimeters, something like that. Okay. Any questions about the process of diagonalization? So again, we're not going to prove the theorem. It's a bit long and needs some reminders from the previous course. We'll be fine if we only know how to do it, not just proving it. And on the other hand, if it was example A, let's have a look at example B, a matrix that cannot be diagonalized. How do you say it? Diagonalized, something like that. Of course, one can give the example we saw before the break, a matrix without eigenvalues above R, for example. But let's look at different, more gentle example. Let's say A is the matrix 1, 1, 0, 1. Again, this is a triangular matrix. So the eigenvalues are the elements of the diagonal, which is just 1. For the eigenvectors, we solve AV is lambda V, which is right now. I can control C, control V from here. Why shouldn't I? Control C, control V. Yes. It is 0 and 0, and it's 1. It is x plus y, and y equals over here. Now we only have lambda equals 1 as an eigen value. For lambda is 1, we have x plus y is x, y is y. From the first equation, we have y is 0. And the vectors are eigenvectors. And the eigenvectors are x and fs 0, for example. 1, 0. Now, no matter how hard you try, you won't get the basis of R2 using only eigenvectors. Here, we don't have a basis of R2 or whatever the field is, containing only eigenvectors. When it comes to linear dependency or independency, we have only one vector, x and fs and 0, eigenvectors. So A is not diagonalizable. So sad. Specifically for matrices of that shape, 0 and 1 above the diagonal, one can think of at least a recursive relation for finding its high powers, but not now. We'll meet it again ahead of the road of the course. Yeah.
Okay, so that one of the values was 1 because y equals lambda y, and the other one we just can't solve.
No, the eigenvalues we get before we solve the equations for the eigenvectors. We get the eigenvalues using the determinant of lambda I minus a equals 0, the characteristic polynomial. Specifically here, because the matrix is triangular, the eigenvalues are the elements of the diagonal. So just write down as 1 and 1. Any more questions? Okay, so I want to briefly mention that we can do the same with said write a note or something. We can do the same with linear operators, T that goes from V to V. Let's write down shortly. Let V be a vector space over a field F, and let P from V to V be a linear operator. Operator is transformation between the same from V to itself. So I call operator. Lambda in F is called an eigenvalue of T if there is a non-zero V in V such that T of V is lambda V. Instead of A, it's just T. And V is called such V is called an eigenvector corresponding to the eigenvalue lambda. If we actually want to find such eigenvalues, we can think of the matrix or a matrix representing T using some basis B. In order to find such eigenvalues of an operator T, we can look at the matrix T from B to B for some basis B of V and find its eigenvalues and the next step, finding its eigenvectors, it's the same. And meaning write down in different color. So I just want to talk about it briefly about the equivalent case of operators, not just matrices. I mean that lambda, oh, come on. Lambda without the slash is an eigenvalue of T if and only if lambda is an eigenvalue of the matrix T from B to B that represents the operator T with the base with respect to the basis B. So whatever we want to say about linear operators, we can say about the respective matrices. When it comes to finding the eigenvalues, and similarly, it's with an I or not? I mean, you need an I here? I mean, it's the same. Oh. Similarly, for eigenvectors, I mean, V satisfies TV is lambda V, if and only if it satisfies the matrix T from B to B, V is lambda V. So one does not actually have to talk about linear operators. He can do all the talk with matrices and he is going to be fine. We can say the same thing about diagonalization. Furthermore, let's write down nicely. Furthermore, we can say that T is diagonalizable if and only if there is a basis B such that the matrix T of B to B is diagonalizable. No, is diagonal. Sorry. There exists a basis such that the matrix is diagonal. And it is true if and only if for every basis at every with bold for every basis B, T B to B is not diagonal itself. but it is diagonalizable. Diagonalizable. So, in the bottom line, when it comes to a linear operator, not a matrix, how do we, first of all, check if it is or not diagonalizable? And secondly, if it is diagonalizable, how do we find the the D and the P, the matrices that we're looking for? We actually looking at some representing matrix of T, choosing any basis you want, and have the matrix T from B to B, and go through the diagonalization process of matrices that we mentioned and show before. Yet again, I'm not planning of proving this. It needs a lot, not a lot, but it needs some reminders from the previous course. Which was a long time ago. Yeah. And we are already short of time. I want to use it for different things. Any questions? One last thing about operators. Um, one last thing for now, yeah. We can define the characteristic polynomial of an operator, again, using the characteristic polynomial of some matrix B. The characteristic polynomial of an operator T from P to V is, let's write it down, P of T of X is P of the matrix T from B to B. Of X for some basis B of V for every basis B. Let's write it down a bit differently. We get the same result, of course. The same polynomial P for every basis B. I'll explain it shortly. What do I actually say here? I say the following. If you take two different bases, B and C, for every basis that you write it in plural, I think it is, bases B and C, we have the same characteristic polynomial for the representing matrices of T, one with B and one with C. Why is that? Matrices T by B and T by C are similar, as you did see in the previous course. I'll explain why. The Cayuse. How do we move from one matrix, one representing matrix, to the other? Do you remember?
By the identity of C, right?
Yes, we multiply it by the in Hebrew it's called matritzat ma'avar. I don't know how you exactly say it in English. Um, check it out. Hold on. We have the time. I'm counting on Wikipedia, yeah. Change of basis. Okay, that's a stupid name. Change of basis um, in terms of linear maps. No. Okay, it's a weird one. Let's look for French. Maybe it's French. I understand it. Français. Yeah. Chemin de Besset. No, it's the same. I don't know. How it errors called? What? The matrix. I B to C. No? Okay. But as far as I understand, as tool from Erez and Neil, you did see the concept of matrices representing um, linear transformations, especially operators, and matrices, a matrix of base changing or something like that. That's I going from B to C, and then from C you have to go back to B, so you multiply it by I from C to B, and one of the properties these matrices is that I from B to C is actually the inverse of I from C to B. And this is, yes, but corresponding to the bases B and C, which means that if you multiply any coordinate vector by the basis B with this matrix, you'll get the coordinate vector of the same vector with, yes, corresponding to basis C. I mean, I, BC, you multiply it with the coordinate vector, you get the coordinate vector, but by the different base. And we define today the similarity between matrices. If one matrix is P minus 1, they are similar. As we said before, that's actually the matrix P for the definition. And as we said, and we said that similar matrices have the same characteristic polynomial. So it doesn't matter which basis you choose to work with. The matrices can be different, but the characteristic polynomial and everything else that is important to us, the eigenvalues and determinant, etc., will be the same. So this one bit long note stating that everything we can say about matrices, we can say about linear operators, and with the same methods. Basically, looking at the corresponding metrics of the operator and working with it. Things that you already did in the previous course, not with our specific subject of determinants and such, but every time we want to, I don't know, check if find the image of an operator or find the kernel of operator and so on and so on, we use matrices, putting in rows, finding the zero row, and such. Okay, was as mentioned a long So very long, but a long note. Any questions?
So you're saying that no matter what the basis is, you say you just think here that for whatever base we could say again.
Eigenvalues, eigenvectors, characteristic polynomial, everything we mentioned will be the same. The matrices can be different. I mean, similar is not equal. But from our point of view of eigenvalues, eigenvectors, characteristic polynomial, and so on, they are basically the same. I mean, in our example, the matrix A, which is 1607, is similar to 1007. They're not the same matrix, A 6, A 0, but they are similar, as we define it today. Any other questions? So we're almost out of time. Don't think we need to write down another thing, so we can finish here. Next week, that's will be Brim Bezat Hashem. We'll continue. As I mentioned, we need to discuss, on one hand, the power of the lambda minus in the characteristic polynomial when eigenvalue appears more than one time. And on the other hand, the number of free variables in the system of equations, AV is lambda V. The connection between these two numbers are very interesting, very important, and that will be our next topic. Any questions before I shut down the recording? Okay. Bye-bye.